So this chapter has basically three sections majorly, if you see, right? And accordingly, those three sections we will be revising it. Like if we talk about first section, so that totally based on the galvanic cell, and the second section is basically the electrolytic cell, and the third one is the conductance. Okay, conductance basically the electrolytic conductance. Right. So galvanic cell and electrolytic cell, all of you are aware, right? So these are the electrochemical cell which convert the chemical energy into electrical energy or vice versa. So galvanic cell convert the chemical energy into electrical energy, and this electrolytic cell converts electrical energy into chemical energy. This is a spontaneous process, and this is a non-spontaneous process. Correct. So starting with the first part of it, which is galvanic cell. So we'll directly take the question, and according to that only we will revise the part, right? So, so for example, if you have a complete cell, then how to find the E cell, or you can say like E naught of cell. So we know galvanic cell is made up of what? Anode and cathode. So anode, basically on anode we see oxidation happen, and at cathode reduction happen. So for anode we use oxidation potential, and for cathode we use reduction potential. For both also we can use either the oxidation potential or the reduction potential. But this is a like you can say more convenient to use in order to find the E naught of a cell. So when you talk about anode and cathode combination, these are basically what? These are basically the half cell reaction, oxidation half reaction and cathode half reaction. They both combine to form the a complete cell, electrolytic cell, right? And for that electrolytic cell, how are you going to find the E cell? So that is E naught cell will be what? Combination of E cell of anode and E naught cell of cathode. And if you see at anode, oxidation happens, so you need to take oxidation potential of anode, or you can use reduction potential of cathode. Take the sum, and that will be your answer. If you want to use both oxidation potential, so you can take oxidation potential of anode minus oxidation potential of cathode. And if you want to use reduction potential, so you're going to use E naught reduction potential of cathode minus E naught reduction potential of anode. So these are three formulas to calculate the E naught cell. Correct? Yes or no? Tell me. So if I ask you one question. Okay. Write the cell reaction of following. So first write the cell reaction of these, which I'm writing over here. First, PP, Fe2 plus, Fe3 plus, and these salt bridge. Then comes the H plus, MnO4, aqueous, Mn2 plus, aqueous, and bloody. This way. So can you write the cell reaction? So are you trying, or should I do first? Then you're going to try for other what?
I will do it.
Okay. So whenever we write this way any cell, this is your basically the anode, this is your bridge, and this is your cathode. So to just remember, we use this ABC type formula. A for anode, B for bridge, C for cathode. This way you're going to write. Correct. Always remember this platinum is basically a surface, inert electrode surface, and it always going to be used when you are making an electrode of ions or gases. If gas is there as a like uh, any chemical reagent in the cathodic side or the anodic side, you're going to use platinum. Or if only ions are there, then only going to use platinum. Otherwise, no need for platinum. You can directly use the electrode. Fine, do it. Done. Mhm. Mhm. So first you need to write the half reaction of anode and the cathode. So at anode, what is happening? Oxidation of Fe2 plus to Fe3 plus. Write it down. So Fe2 plus going into Fe3 plus, and obviously it's going to lose the electron down. Then only like this will going to form. Now for this, if you see MnO4 minus going into Mn2 plus. So MnO4 minus going into Mn2 plus. So if you check the oxidation number of Mn over here is plus 7. So how many electron exchange will be there? 5. So it need to take 5 electron, then only Mn2 plus will going to come. Now balance the oxygen. 4 oxygen there. So 4 H2O you going to use. And to balance the H2, you use hydrogen. So 8 H plus will be there. And if you check, this is the balance equation. Now you need to add these two to make the final cell reaction, right? How are you going to add? By multiplying this equation with 5. Why? Because you want to cut the common electron out, not to take the common electron into the final reaction. Okay. So on doing it, what are you going to get? See this. So 5 electron will going to cancel out from this to this. Anything else will going to cancel out? No. So you can write the final reaction. It will be 5 Fe2 plus MnO4 minus 8 H plus, giving you 5 Fe3 plus Mn2 plus and 4 H2. That's it. That will be your final reaction. What about B? Yes. So now this is your anode and this is your cathode. Oxidation will going to be happening of chlorine gas. So if Cl2 get oxidized, not chlorine basically. So if you want to do the oxidation, then oxidation of Cl minus will going to be there, right? Cl minus form the what? Cl2 and 2 electron, right? And if you see cerium plus 4, it will take 1 electron and form cerium 3 plus. Again, you need to multiply this reaction with 2. Why? So that common electron get cancelled out. So ultimately, what are you going to get? you're going to get 2Cl minus plus 2 cerium 4 plus, giving you Cl2 plus 2 cerium 3 plus. That will be a final reaction. This is how you get to it. Am I clear? Yes or no? So as I told, platinum over here will work as an inert electrode. It's just a surface to provide uh, like for the process of oxidation or reduction. Okay. But if you use any metal electrode, like if zinc are using, copper we are using, so zinc and copper along with the surface for the oxidation and reduction, they also take part into the reaction. So these electrodes are known as active electrodes. Correct. Function of salt bridge, you know, right? That you can. Moving on, say for example, okay, do this question. Let's talk about E naught. Say E naught of Zn 2 plus and zinc is minus 0.762. E naught of Fe 2 plus and Fe is minus 0.44 volt. And E naught of copper 2 plus copper is 0.34. Now the question is, the first part I take, how many cells can be formed? How many cells you can form out of this? Okay, and also find E naught of cell. That is first part. Second, then comment on find, you can say maximum E naught, which of the cell going to make maximum E naught and what it will be, and also minimum E naught. Do it, and I need answer this time. Siddharth,
Yes, sir.
you want to be free early?
Oh, yeah.
Then you have to answer quickly, right?
Okay, I'll tell.
I think like it won't take much time. See, 5 o'clock. 5. See, 8:30 is the end time, right?
Yes, sir.
Okay. So if we go with a good pace, if I end it by say 8 o'clock, will it be fine?
Okay. Yes, sir. Fine.
Okay. Yes, guys, doing or not?
Oh, yeah. Sir, you can form three cells.
We can form 3 cells. Okay.
Yeah.
And what all these? If I say first one, that will be the combination of, just say like,
You.
this is anode and this is cathode this way. So what
Uh,
should I make as anode?
Anode you can make as. 1 second.
Mhm.
Yes, sir. Anode you can make as Fe2 plus Fe.
Fe2 and Fe. This is what you're saying. So anode basically oxidation happens. So if I write oxidation
Yeah.
potential, I'll be writing in this way. Correct?
Yes, sir. Yeah. And then cathode, you can write Cu2 plus Cu.
Cathode, which is already written in reduction potential part. So I'll be writing this way. So E cell for this will be what?
Uh, it'll be 0.78.
0.78 because Fe2 plus, if you see, it will be negative of this what is given. So negative of 0.44. Why? Because this is the reduction potential which is given, but we are taking oxidation potential, so obviously it's going to be the opposite of it, plus reduction potential of cathode, which is already given to us as 0.34. Now it is coming out as 0.78. Okay, first cell. Then
Next cell, you can do the same with Cu2 plus Cu and Zn2 plus Zn.
so E naught Zn2 plus we can take as anode. This is what you're saying, right?
Yes,
And
sir.
copper as reduction or the cathode. So again the same drill. I'll directly taking it as positive because negative is given, which is reduction potential. I'm repeating. I need to take oxidation, so that will be opposite of it.
Yeah.
And then 0.34. That comes out to be 1.1.
1.1.
This combination is known as, this is basically a what, galvanic cell, but it has a one proper name. What it is? Daniel cell. We call this combination as Daniel cell.
Yes, sir.
Then third,
Third will be E naught Zn to Zn2 plus and E naught Fe2 plus to Fe.
so E naught Zn2 plus and E naught, which part?
Fe2 plus to Fe.
Fe2 plus. Now this is 0.76, and that is if you take Fe2 plus, like we should take
It'll
the
be
reduction.
minus 0.44.
So Fe plus 2 to Fe, and that will be minus 0.44, right? So
Yes,
that
sir.
comes out as 0.32.
0.32.
0.32. See, all three are possible. Why? We are saying galvanic cell should be spontaneous in nature, right? And for spontaneity, we need to check del G value, and del G value should be negative. Now, if you know the relation between the del G and E naught, that is plus NF E naught, correct? Now, to make this del G naught negative, E naught should be what? Positive. So this is the criteria to select the cell. Your value should not be negative. This final value should not be negative. It should be positive. Then only you're going to get a working cell. Okay. This is how you're going to approach this question. So you need to identify which out of three going to be used as oxidation potential and the reduction potential. And the combination should be the positive. Are you getting it what I'm saying? Guys, yes or no? Tell me. Now from here only you can decide which will going to the maximum. So this value is maximum and this value is minimum. That is the second part of this question. Understood, everyone? Say yes or no.
Yes, sir. Yes, sir.
Yes, sir.
Now one more question. If E naught of Cu2 plus Cu plus platinum is 0.15 volt and E naught of Cu plus to Cu is 0.52 volt. Now find E naught of Cu2 plus to Cu. Okay, we know this value, but we need to find it out by using the given potential. So what will be the value of Cu2 plus to Cu? That you need to find out.
Sir, I got it.
Yes, what it is?
0.345.
0.345. Okay,
Yeah.
should be that only. So how are we going to do it? See this. So if I write this, what is given to us? Cu2 plus going to Cu plus. It's what? Basically reduction. So can I write this reaction as Cu2 plus electron giving you what? Cu2 plus. Then second equation, if I see, I can write it as Cu plus electron giving you what? Cu, correct? That is plus 1. Okay. Now what we need to obtain? We need to obtain how we can get it Cu2 plus giving Cu by taking 2 electrons. So we can easily see we need to just add these two reactions, right? So if you add these two reactions, this will cancel out. You're left with Cu2 plus 2 electron, giving you what? Cu. Now E naught for this is given as 0.15 and E naught for this is given as 0.52. Can we directly add these to find the E naught of this? Huh?
No.
No. Correct. Because basically, if you talk about cell potential intensive property, right? We cannot like directly add them. But if they were extensive property, we can easily add it. Then how are we going to do it? We're going to use this del G. Del G is what? Extensive. So we can take the help of del G. So what we're going to do? We're going to find del G1 for this, which is nothing but minus NFE. And similarly, del G2 for this minus N2F and then this is the del G for this reaction. Okay, so that will be N3FE3. So just put it over here. It should be negative. So del G reaction will be that you can add del G1 plus del G2, right? So there will be minus N3FE3 and minus N1FE1 and minus N2FE2. So from this, Faraday get cancel out. N3 you see number of electron involved. So 2 E3 and you can end this negative as well. So it becomes positive 2 E3 equal to N1. In this case, how many electron? 1. So that will be E1 plus. In this case, how many electron? Again 1. So that will be E2. So from here, E3 will be what? E1 plus E2 over 2. So 0.15 plus 0.52 over 2. And that comes out as 0.67 divided by 2. That will be 0.335. Isn't it? Or you can say 0.34. This is how you're going to solve. Okay. So whenever such reaction comes, like in the final reaction, you see the electron presence, then always go for del G. Okay. And if you want to save the calculation and if you check the final reaction, there is no electron involved, then all the common electron get cancelled out, right? So all common electron, these electron will going to be cancelled out. Then what are you going to left with? E3 equal to E1 plus E2. Then you can directly add. Okay. It doesn't mean like it become extensive. No, it doesn't become extensive. It basically the number of electron involvement become equal. That's why it is coming as this way. Am I clear? Yes or no? Moving on after this is Nernst equation. Okay. The next part of it. So let's talk Nernst equation. Yes. Any doubt? Anyone? Yes, Trisha.
No, sir, nothing. Join us.
Okay. Now, next question if I ask, but before this Nernst equation, if we talk about what is Nernst equation? So it gives you the EMF of cell. EMF of cell at any concentration. Okay. Or you can say this gives you the non-standard EMF. standard EMF of cell. So there is one E cell and there is one E naught cell. So this E naught cell is the standard and this is non-standard. So this is given by this formula, E naught of that cell minus 0.0591 divided by number of electron involved log Q value. What is this Q? Q is basically the reaction quotient, concentration of product over concentration of reactant. Correct? Okay. Then question which I'm going to ask is find half cell potential of following. First part, this is the half cell, Mg going into Mg 2 plus and 2 plus magnesium 2 plus ion concentration is 2 into 10 to the power minus 3 molar. And E naught of this electrode Mg2 plus 2 Mg is given as minus 2.36 volt. Calculate E cell of this. And this is at 298 Kelvin. Then only this factor is coming 0.0591. Okay. Now do it and tell me what will be the value. Second part we can do is calculate for this Cl minus Cl2 platinum. And the concentration is 10 minus 2 molar and this is 1 bar. If gas, see gas is present in the electrode and nothing is given about the electrode, oh sorry, that gas, you can take 1 bar. That will be the standard condition for it. What if I ask you cell potential for complete cell? After doing these, solve for this C part. What it is? Okay, I haven't given the E naught of this. So E naught of Cl minus Cl2 Pt is 1.35 volt. Find E cell of platinum H2 gas CH3COH aqueous MnO4 minus Mn2 plus H plus platinum 0.1 molar 0.1 molar. Talk about this 0.1 molar again, and this is 10 to the power minus 2 molar. And K of acetic acid is given. What it is? 10 to the power minus 5. I think, yeah. What else you need? You will be needing E naught of this reduction, half. So E naught of MnO4 minus Mn 2 plus H plus platinum. It's basically 1.5 volt. So you will be seeing how I am representing. Like whenever there is a phase change, I'll be using this slash, right? Single bar. The gas is there, aqueous is there. So phase changing is there. To separate them particularly, I'll be using that separate one. But whenever there is no phase change, these all are in aqueous. This is also in aqueous. This is also in aqueous. This is also in aqueous. So I am just using comma to separate them. So that also you need to include while you represent the cell. Okay, for the first one, I hope every one of you have done this. Tell me, what will be? So E cell for this will be E naught cell minus 0.0591 divided by n log Q, isn't it? So this will be what? So first of all, you should have the idea like how many electrons are involved and how this reaction goes. So from magnesium to magnesium 2 plus. So magnesium 2 plus, it will give the 2 electron. Correct? Now, E cell will be what? E cell will be E naught cell. This is oxidation. So you need to take the oxidation potential, but it is reduction potential given to you. Changes into oxidation potential. So you need to just make it positive. So 2.36 minus. Then I take 0.06 instead of 591. And number of all 2, put 2 over here. Then log Q value will be what? You have just this as ion. This will be what? Solid. So solid we're not going to include. We're going to include Mg2 plus. So how much the concentration of Mg2 plus given? 2 into 10 to the power minus 3. Solve it. So it comes out as 2.36 minus 0.03. And that will be what? That will be minus 3 plus log 2 means 0.2. So you're left with 2.7 minus 2.7. So 2.36 minus, this minus become plus. So 0.03 into 2.7. Just calculate it. What is going to come? 2.36 plus. If you multiply this, what are you going to get? 0.06, near about, or this only. So it become what? 2.42, isn't it?
Yes, sir.
Okay. So 2.42 will be the value. Now for the B option, for option B, oh sorry, the question B, then what will be the value? How are we going to do it? Has anyone solved this question B?
So 100.
Okay. Again, first you need to write the reaction and check like how many electrons are involved. And writing the reaction will going to help you to find the Q representation, right? So that you can have the idea, okay, where are the product, where are the reactant, you need to take the ratio of it, right? So what will be the reaction? What it is given basically, if you check, Cl minus 2, Cl2, platinum. Platinum is on the right side, it is basically a cathode. Okay, on cathode, what happened? Reduction happened. And for reduction, if you see, it will happen for Cl2 gas. This is what very important, like to identify this way. Okay, so if half of the cell is given, so you need to look for the electrode. Where is the electrode? If it is at the extreme right, then cathode. If it is on the extreme left, then it will be anode. So Cl2 will reduce itself half by taking 2 electrons, correct? By taking 2 electrons, it will form Cl minus 2 Cl minus. Then from here, Q value will be what? Q value will be concentration of Cl minus square divided by partial pressure of Cl2. Okay. Then find the E cell. E cell will be E naught cell minus 0.059 and log Q. Now that will be E naught is given to you. E naught is given to you 1.35 minus 0.06 divided by 2 electrons are involved log Cl2 square. Cl2 concentration 10 to the power minus 2 square divided by partial pressure of Cl2, which is 1. So from this two cancel out, and log 10 to the power minus 2 is minus 2. That become plus. Yes, somebody has doubt or what?
Sir, how is chlorine getting reduced, sir? It's getting oxidized, right?
No, bacha. See, this is what I told. Like representation will be in this way, so you may feel like this is happening, like Cl minus going into Cl0, which is kind of oxidation. But this is not oxidation. We need to check this in this way, like the electrode part. So if electrode is the extreme right, then this is cathode half. And we know at cathode half reduction happened, isn't it? Isn't it?
Oh, okay, yes, sir.
This will going to be confusing when you have gaseous electrode most of the time, and especially when such gaseous electrode is there, like halogen gaseous electrode. So that time you may get confused about it, like okay, reduction is happening, oxidation is happening, because representation will going to feel you like okay, the oxidation happening, but actually you need to figure it out with the electrode, where the electrode is present. Over here, electrode is platinum. If platinum is in the extreme right, then it is your cathode half. If it is extreme left, like if I take this representation in this way, platinum, Cl2, then Cl minus. This is anode. Now you may feel like Cl2 going into Cl minus. No, then you feel then you say like reduction is happening, but no, this is anode and oxidation will take place. Am I clear?
Yes, sir.
So if you add these two, you're going to get 1.47 volt. So that will be your answer. Now solve this. Option C. Everyone got this value correct? Yes or no? Yes, yes. Now this is a complete cell. So you have anode, you have cathode. So you need to write both the reactions, then write the final reaction, and accordingly you're going to write calculate the EMF of the cell. Am I clear? Okay. Is there anyone who is trying? Or you already gave up? Guys? Then I'll solve and you just go through it, check whether you are giving the right approach or different what. Okay, see how we're going to do it. So I have used multiple concepts over here in this question. So it will give you the idea like how we're going to deal such kind of questions. So first of all, it's a complete cell. So first we take the anode. So at anode, if you see what is happening, it's a hydrogen gaseous electrode, right? Because the standard hydrogen gas electrode is there. So if you talk about anode, oxidation happen, and oxidation of hydrogen will be like H2 going into H plus. Correct. Then electron will going to be used out. So 2H plus 2 electron. And if it is standard, then E naught for this will be what? 0. Correct? For hydrogen standard electrode. Now this H plus concentration will be the concentration of this acetic acid. Okay. Why I'm saying like this as a different? Because you will get H plus from here in the second half. So I'll take it as 1. Okay. Then for cathode, so we have written this Mn4 plus Mn2 plus electrode previously. So I'm just writing directly MnO4 minus plus 8H plus 5 electron, giving you what? Giving you Mn2 plus and 4H2O. And for this, E naught is given to you, right? Which is 1.5, right? Okay. Now the thing is, if you add these two, and you need to add in such a way so that common electron get cancelled out. So multiply this equation by 5 and this equation 2. So 10 electron get cancelled out. Final reaction will be what? 5H2 plus 2MnO4 minus plus 16H plus, and this is the cathode concentration. Remember this. This is your anode. Anything else? No. Giving now 5 to 10 times. 10 times H plus, that is anodic H plus Mn2 plus. No, 2Mn2 plus 8H2O. Correct? Correct. Now for this, E naught will be what? As I told, is there any reaction in the final reaction? No. So you can just add these two. So if you add this, E naught of cell will be what? Nothing but 1.5 volt. Okay. Now EMF of cell will be what? E naught of cell minus log of, minus 0.0591 divided by N log Q. So Q value is also like very interesting over here. Why? H2O liquid we are not going to consider, but we're going to take this Mn2 plus square, then in the product H plus to the power 10, that will be anodic, divided by, come to this side, H plus 16 power cathodic concentration, then you have MnO4 minus square, and then you have partial pressure of H2 5 times. Correct? This is what you need to include in E. Now everything is given to you in the question. So put it over here. It becomes what? 1.5 minus 0.035 take, and how many electrons involved? So 5 times 10. How many electrons get cancelled out? 10. So N value will be 10. Log of Mn2 plus concentration. Mn2 plus concentration is this 0.1. So 0.1 can be written as 10 to the power minus 1 square. So it will be 10 to the power minus 2 into H plus anodic concentration. Anodic concentration is this. Now, can you tell me how much H plus will be there? Will it be 0.1 molar? No, because this is a weak acid. Weak acid. CS3COH, weak acid. So for weak acid, H plus concentration is basically C alpha, which is written as root Ka times C. And Ka value is given to you 10 to the power minus 5 into C, 0.1. 0.1. It becomes 10 to the power minus 6. Take the root. It comes out as 10 to the power minus 3. That will be the anodic concentration H plus. That is also important to look up before putting the value. Okay. Now anodic concentration 10 to the power minus 3. And that is 10 times. So it becomes 10 to the power minus 30 divided by cathodic concentration. Can I take cathodic concentration as, what will be the cathodic concentration? That is your totally like the H plus concentration. Okay, 10 to the power minus 2. So over there is nothing weak acid type of thing. So 10 to the power minus 2, 16 times it becomes 10 to the power minus 32. And then MnO4 minus concentration is MnO4 minus concentration 10 to the power minus 1. Take the square, it become 10 to the power minus 2. And partial pressure is not given to us, then we can take 1 to the power 5. So from here to here, this cancel out. If you take this 10 to the power minus 2, it goes up, it becomes 10 to the power 2. So from this to this 5 times goes up. Correct? So what you left with? You left with 1.5 minus 0.006, right? So just subtract this value, there will be your answer. isn't it? Tell me yes or no.
Yes, sir.
Okay. Now moving on. Moving on. If you have any doubt, you can ask me, guys. If you have any doubt, you can ask me before I give the next question. No doubt. Okay, write down next question then. Hmm. Find cell EMF of platinum Cl2 KCl HCl Cl2 platinum. 1 atm for this, 10 to the power minus 4 for this. Here it is 0.1 and 2 atm. Yeah, solve. Don't take more than 2 minutes. Done. Guys. Okay, this is your anode part, this is your cathode part, right? And can you see they are the same electrode? And when you have the same electrode, that type of cell is known as concentration cell. Okay, so concentration cell basically galvanic cell only when you have the cathode and anodic half made up of same material. And this is one of the examples. And keep in mind, whenever we talk about concentration cell, E naught of this cell is 0. Why? Because say E half of this half cell is X, then that will be minus X. If you take the sum, it comes out to be 0. Correct. Moving on. That's why E naught was not given for each half. Now, the thing is, you should write the anodic half and the cathodic half first. So for oxidation, Cl minus will be there. Cl minus will go into form Cl2 by losing the electron. So it should be 2Cl minus. Then write the opposite of it. Cl2, 2 electron, giving you 2Cl minus. Now this Cl minus is basically the anodic half, and this Cl minus is cathodic half. Similarly, this is anodic and that is cathodic. This thing you need to write it down. Why? Because in order to find the Q, that will like give you trouble. So that side you have, okay, first add them up so that you have the final reaction. This get cancel out and nothing else will going to cancel out. You cannot cancel this by this. Why? Because their concentration are different. Are you getting it, guys? And similarly,
Yes, sir.
you cannot cancel this by this. So ultimately you're going to write Cl2, which is from the cathode, and 2Cl minus, which is from the anode, giving you Cl2 from the anode, giving you 2Cl minus from the cathode. Q value from the cathode square into partial pressure of Cl2 anode upon Cl minus square anode partial pressure Cl2 cathode. So E cell will be what? E naught cell minus 0.0591 divided by n log Q. Now this value is 0, so you left with minus 0.06 divided by how many electrons? 2. Log of Cl minus cathode, which is going to be from HCl. So 0.1, 10 to the power minus 1 square. So it becomes 10 to the power minus 2. Pressure Cl2 anode, so which is this 1 atm. So that will be 1 divided by Cl minus anode, which is 10 to the power minus 4 square. It becomes 10 to the power minus 8 into pressure of Cl2 cathode, which is 2 atm. So into 2. So that comes out to be what? 10 to the power minus 6 goes up 10 to the power 6. To take 110 out of it, it becomes 10 to the power 5. And if I take 110 out of it, it becomes 5 into 10 to the power 5. Now the value will be what? Minus 0.03. Log value will be 5 plus log 5 is basically 0.69. Correct. So if you multiply this, you're going to get what? How much the value you're going to get? 5.7 you can take, right? And 3 times of 5.7. 171 decimal. So that will be the value. Okay, that will be E cell of this. So concentration cell. Clear? So you can see the value is negative. So will that be a functional cell? No. Okay. So negative value is a non-spontaneous cell. You should have taken otherwise, then only it's going to be a workable functional cell. Clear? Any doubt? So like so far, whatever we have done, tell me.
No, sir.
Now, basically we have various half cells So how many types of half cells we have? If we talk about, that is also one important point, like topic in this chapter. Various half cells. So you have first type of half cell as metal ion half cell. Okay, metal ion half cell. As in you can take like zinc going into Zn2 plus. This is metal ion half cell. And you can use it as anode, as cathode, depending upon what is the other part of it, right? So it doesn't mean like if it has a positive oxidation potential or positive reduction potential, you only use it for the oxidation half or the anode or the cathode. No, it doesn't go this way. Basically, you compare the two electrodes, which one has the highest reduction potential, that will be used as cathode, and which has the highest oxidation potential, that will be used as anode. The second half cell is basically redox half cell. And in that, only one ion going into the other ion. As in you can take, if you remember that half cell we have taken MnO4 minus going into Mn2 plus, H plus, platinum. This is a redox half cell. Fe3 plus going into Fe2 plus. This is also a redox half cell. Okay, so redox half cell will be like this. You need to use platinum with it. With redox half cell, always inert electrode will going to be there because only ions is present in the redox half cell, and that requires surface, and for that we use platinum. If you see the representation of redox half cell, it's going to be this way only. Then comes the gaseous half electrode or gas electrode. Third type is gas electrode, like standard hydrogen electrode, SHE, basically. That is one of the kind of gas electrode, like chlorine half cell we have used, right? So for example, if I take it PT, Cl2, Cl minus, okay, this is anode. Similarly, I can take what? Hydrogen, PT, H2 gas, HCl. Okay, that is also anode. And on the same way, you can write their reaction and find the EMF as well. If they work as anodic half cell or cathodic half cell, accordingly you need to write the equation, and accordingly you need to find the EC. Then comes the important one, very important. And this is like challenging for most of the students. What it is? Can anyone tell me what I'm talking about? The fourth type of half cell. Metal insoluble salt anion half cell. This is important. And why it is important? Because it become very complicated when you write the cell reaction for this. How you going to write the cell reaction, and then how you going to find the EMF of the cell or E naught of the cell. That is also very tricky in this case. Okay. So I'll give one example. So you need to have a metal, then you have a metal insoluble salt anion. That will form the electrode. Like if I am taking silver as a metal, then I need to take a insoluble salt of silver, and that will be what? AgCl. And this salt, whatever the anion, that anion should also be present. So anion of this salt is Cl minus. So Cl minus should also be present in the solution. So how are you going to make the half cell electrode? So first you take the Ag as a metal electrode this way, and then there is a coating. Coating of what? Insoluble salt. This is the insoluble salt which we need. AgCl, insoluble salt. And this is Ag, electrode. And it is dipped into the ion and or a electrolyte which has a common anion. So it can be any electrolyte, but it contains Cl minus into it. Like you can take KCl. And thus it's going to form a metal insoluble salt anion half cell. So I should give a dash over here as well. So metal, metal insoluble salt, anion half cell. Can we take any other example? Yes. To take lead. Now you need to take insoluble salt of lead, which is PbSO4. You can take. Okay. And if PbSO4 you have taken, then its anion should also be present. So SO4 2 minus in aqueous. This is how you're going to represent this cell. Are you getting it? Now, if I take this as an example and say if I have made this as an oxidation half, then how would I write its reaction? Okay, see this. If it work as a anodic half cell, then your metal Ag solid, it's better to take first reduction half cell, then only it's going to be more easier to give you the representation of it. So if I use it as a reduction, okay. So from AgCl solid, it takes the electron and then it forms Ag solid. So just assume it is the plus which actually takes the electron and form the Ag solid. What is happening? From plus to 0 you are going, it's a reduction. And then what left? Cl minus. This will be the reduction half cell. If I write the oxidation, so I need to just reverse it. So you have Ag solid and Cl minus from the solution. It will give you AgCl plus electron. That will be oxidation half of it. That will be the oxidation half of it. Correct? Correct. Now, how to find the E naught of this cell? That is also not pretty easy. Okay, then sir, how are we going to do? See over here. So let's find the E naught of cell. Okay. First of all, we have AgCl giving you like this is the reduction half cell I'm writing AgCl electron giving you Ag and Cl minus, right? And then you can just a minute, like we need to get the, this is the half cell we are using, right? This is the half cell we are using, cell half. And what half it is? Reduction half. Reduction half cell. Now to make this reaction, we will be using first the simple Ag electrode reduction half cell. And for this, we know the E naught value, E naught of Ag plus to Ag. Okay. And let's say we want to find the E naught of this, right? So we have this, then we need AgCl solid, right? Ag plus we have AgCl solid we need. So AgCl solid, if it is sparingly soluble, it will going to give you what? Ag plus and Cl minus ion. Yes or no? And for such reaction, we have what? Ksp value. Correct? Now, if you add these two reaction, so from Ag plus cancel out, what you left with? You left with AgCl solid plus electron giving you what? Ag and Cl minus. See, this is what we need and we got it. Now, in order to find the E naught of this, we will be using del G of this reaction. And that will be what? Minus NF E naught of Ag plus Ag. And what will be the del G naught? Like if you see del G of this is minus NF E naught of Ag plus Ag. Fine. Now what will be the del G of this? So you remember that minus RT, or you can take 2.303, right? Instead of ln. So that will be minus 2.303 RT log KSP. Isn't it? So del G of this reaction will be what? Minus NFE and minus 2.303 RT log KSP. Now just simplify it. Simplify it. What we are finding? We are finding E naught of this. So basically, if I write it, I will be writing as minus 1 into F, and this will be the E naught of what? E naught of Cl minus AgCl Ag, because it's a reduction half cell. Then minus, in the first equation, one electron again, F E naught of Ag plus 2 Ag minus 2.303 RT log Ksp. So from this factor goes out, minus goes out, and you're left with F over here. Okay. And if I say n electron are involved, then I can write n over here. So ultimately, I will be having E naught Cl minus AgCl Ag, that is equal to E naught Ag plus Ag and plus 0.059, putting R and T value and F value, n log Ksp. Are you getting it? What I did over here? Guys,
Yes, sir.
I'm telling you, this is very important. Very important. Okay. Now, how to get this Ksp value? Ksp is this for this reaction. Okay, solubility product of this AgCl salt. So that you need to calculate. Fair enough. So this is the half part of it, half cell reaction, and that is the basically what cathodic half reaction. Cathodic half reaction. Anodic half reaction. Anodic half reaction. How are we going to do it? So you need to oppose it, and then you need to calculate the anodic half reaction. And then if you make, or like, is there any question where this this half cell used like their question where cell reaction is there, and in that cell reaction half cell of this metal insoluble anion salt is there, then you need to utilize this over there. Okay, it's not a complete cell. Again, I am saying it, this formula looks like it is for a complete cell. No, it's a half cell reaction only still. So let's try to understand with the question. If I ask you one question, find it out. So the question is, you have first two questions are there. Write cell reaction and find cell EMF. And you have Ag, AgCl, KCl, AgNO3, Ag. If I say Ksp of AgCl is 10 to the power minus 10, and E naught of Ag plus 2Ag is 0.8 volt. Do it. KCl concentration is 10 to the power minus 2. AgNO3 concentration 10 to the power minus 2 molar. Guys, do it. Guys, done.
So 1 second.
If you are done with it, I'll solve it later. First, there is one more thing I need to explain you. That is also important. Like this is for the E naught. What if you're solving it, you solve it and just let me know once you are done. Or should I continue with it? Tell me.
Oh, so I think I'm done.
Okay. So what you are getting? Value. Tell me.
Maybe 0.2.
0.2. Okay. So now see this, the concept, the next part, which is the continuation of it. We have find the standard EMF, right? What if non-standard EMF? Like what will be the just E value? So for example, if you have cathodic half reaction, cathodic half. So cathodic half will be what? AgCl solid, electron giving you what? Ag solid and Cl minus. Now if you find the non-standard of this cathodic half, which will be ECl minus AgCl Ag, correct? That will be what? E naught Cl minus AgCl Ag minus 0.0591 divided by how many electrons are involved in this case? If you see, there is only one electron, right? So let's take like n electrons there. Then log of concentration of Cl minus, concentration of Cl minus. Now, if you talk about this E naught Cl minus AgCl, we have just calculated it, isn't it? What it is? Just go up and check. This whole lengthy value is that E naught Cl. So if you write it over here, what are you going to get? Write down over here. So E naught of E cell, that is given as E naught of Ag plus Ag plus 0.0591 and log KSP minus 0.0591 and log Cl minus. Correct. Now, if I utilize the log property and take this 0.501 common, it becomes E naught Ag plus Ag. And let's say I have taken minus 0.0591 common. Then it becomes log of Cl minus over KSP. Correct. So far, are you getting it? It's again the non-standard EMF of half cell, right? Now see this value. Can we replace this with something? Say for KSP, what we have used AgCl going into Ag plus and Cl minus. Now KSP value from here will be what? Concentration of Ag plus and Cl minus. Now isn't it 1 by Ag plus concentration is what? Cl minus over KSP. Correct, no? So can we replace the Cl minus KSP with 1 by Ag plus concentration? So E naught Ag plus Ag minus 0.0591 n log of 1 over Ag plus concentration. Just check it once and tell me, like, is there any part which is unclear to you? Anyone? Have you done it earlier in your electrochemistry section? This part? There is
No, sir.
no. Okay. This is important. I'm telling you, and most of the student like used to feel what challenging, I will say. So is there any confusion so far? I know it is like if you are studying it first time, it's going to be pretty confusing. There is no doubt about it. So you can watch the recording once again and go through it like what is happening over here. Okay. Now why I have used it? Because of the question we have taken. So over here, just remember this Ag plus concentration. Whenever this Ag plus concentration will be needing, you will be taking KSP over the concentration of Cl minus. This Cl minus from the ion, or you can say electrolyte, whatever the electrolyte is given to you, whatever the concentration of electrolyte, that you're going to consider this. Then only it's going to be there. Write it down and tell me once you're done. And still, if you face any doubt, do ask. In the galvanic cell, this is the most important section. Okay. Okay, one more thing. Can anyone tell me what is this? What is this? Just think and tell me. If I say Ag plus taking one electron and forming Ag, will it not be the same thing? So if I write the non-standard EMF of this Ag plus 2 Ag, it comes out to be the same, isn't it? Guys, tell me. So I can say our E cell minus AgCl Ag can directly written as E of Ag plus Ag. And this is the important relation. Why? Because now you need not to care about what this cell is. You can just write this metal insoluble salt anion as in this form. It become a simple Ag plus Ag electrode. That's it. But this concentration you need to remember. The Ag plus concentration you're going to take, that will be what? KSP over the Cl minus. So don't forget about this concentration of Ag plus, else it will be the same thing only. Once you have this value, E of Ag plus 2Ag, you can directly put it in place of this. You will have ECl minus AgCl Ag. This is what important in this part. Clear? Clear. Tell me. Now, going back to that question. Go back to that question. What it was. This was the question, right? So I'll take it. on a different part of it. Ayyo. How to move this? Okay. Yes. So this is your question. One answer I got as 0.2. Now see this. What it is? It is your anodic half, right? And this is your cathodic half. So anodic half, can I write this as a, this is basically a metal insoluble anion electrode, right? So I will be writing this value of anodic half will be nothing but the Ag plus, correct? And the concentration of this Ag plus, concentration of this Ag plus will be from Ksp over Cl minus concentration. So Ksp is given to you, which is 10 to the power minus 10. And Cl minus concentration is 10 to the power minus 2. So from here, concentration of Ag plus came as 10 to the power minus 8. Now just focus on this part. And this is also what? Ag plus Ag. Now if I write these two reactions, I'll be taking this as Ag going into Ag plus and Ag plus going into Ag. This way I'll be writing. So this part is basically the cathodic part. This part is basically the anodic part. Correct. Now, since both are same, the both will going to behave as a what? As a concentration electrochemical cell. So if I say X is the value or E naught of this, then it will be minus X. So it will cancel out. Okay. So E cell for this will be what? E naught of cell, which is 0 minus 0.0591 over n log of concentration of Ag plus from cathode and concentration of Ag plus from anode. So how many electrons are involved? One only. Okay, like this will give 1 electron, this will take 1 electron, correct? So what are you going to get? Minus 0.061 log of cathodic we have calculated 10 to the power minus 8, and anodic is basically the this one 10 to the power minus 2. So it comes out as minus 6 will be out, so it become plus 0.06 into 6, so 0.36 volt. That will be our answer. Am I clear? This part? Yes or no?
Yes, sir.
Is it clear to everyone? I know it will take some time to digest, but this is how you're going to do it, okay? Then one more thing in that only, then we're going to start our second part of this chapter. Thermodynamic function for cell reaction. Like if cell is given to you, how are you going to calculate the del H, del G, del S for the cell? Okay. So I'll give you the direct values. I won't give you the proof how we reach that, but that is also important. You need to remember for the questions. Like what will be the del G, del H, del S for cell reaction. Okay. So basically del G we know. Del G we know minus NF E cell, right? Now del G also basically what? VdP minus SdT. Remember this. This is an important like equation. You must have remembered del G in terms of minus RTL and K, del G minus NF E cell. These are most like common one. That is one important part. dG VdP minus SdT. This is for any substance. For any reaction, if I write, it will become d del G equal to del V dP minus del S dt, that way. Correct. Now, if I take constant pressure, so at constant pressure, dP will be 0. So from here, d del G will be what? Minus S dt. Again, I'm going into the proof side. So you can take this del G, put it over here, and then you have the del S. So I'm just directly writing del S for the reaction comes out to be NF d of E cell over dt. This is how you're going to calculate the del S. Now, how are we going to calculate the del H? So there is one relation which is, if you remember, del G equal to what? Del H minus d del S. So you know del G, you know del S, you can calculate the del H. So again, I'm writing directly del H will be what? Minus NF E cell, which is del G plus T and F E cell over dt. That is also one formula. Okay. What else they can ask thermodynamically in this? They can ask Cp value as well, del Cp. And from Kirchhoff equation, we calculate it. So I'm again directly writing this NF T second differential of E cell over dt. This way again. This is what I need to tell you about. That's it in this part. So we have done the galvanic part of it, right? Now moving on to the next part of this chapter, which is electrolytic cell. Electrolytic cell. And in electrolytic cell, basically we do the electrolysis, and most important from the electrolysis purposes over here in this chapter is what? Faraday law. So Faraday's law. So first law, basically what it says whatever be the weight deposited on the electrode when you pass any current for a certain period of time, it will be what? Weight will be directly proportional to the charge passed. You can remove the proportionality constant, it gives you Z into Q, which can be written as Z I into T. Okay, W equal to ZIT. Now, what is this Z? So Z is like when you pass, say, 1 coulomb of charge, okay, and whatever be the weight going to deposit when you pass 1 coulomb of charge, that will be your Z. Are you getting it? What I'm saying? So Z is basically the equivalent mass, basically electrochemical equivalent mass. So Z is electrochemical equivalent mass. Okay. Now let's find out what is this and how we're going to calculate it. If I say charge is 1 only, then Z becomes W. W becomes Z when Q is 1. Fair enough. But can we represent it into other form? Yes, we can do it. How? Let's say what is 1 mole of charge? 1 mole of charge is nothing but 1 Faraday, right? And 1 Faraday is 96500 coulomb. So 96500 coulomb, if it deposit equivalent mass, obviously it's going to deposit equivalent mass of the compound. Then 1 coulomb of charge will going to deposit how much? Equivalent mass divided by 96500. So that will be your Z value. Z is basically equivalent of that compound divided by 96500. Okay. So for example, you take aluminium 3 plus and gives 3 electron to it, what is going to form? Aluminium, correct? Now, can I say 3 mole of electrons depositing 1 mole of aluminium? Is it correct or not? Is it correct or not? Now, if I say what or how much weight of aluminum will going to deposit if 1 mole of electron pass, you will say, sir, 1 by 3 mole of aluminum will going to deposit. What is this 1 by 3 mole of aluminum? That is the equivalent weight. Equivalent weight of aluminum is what? Molecular mass of aluminum divided by 3. This is what we are looking. 1 mole aluminum is what? Molecular mass, and by 3 is basically the n factor. And when molecular mass by n factor we write, that is comes out as equivalent weight. So Z is basically the equivalent weight of the compound. So for one charge, this become equivalent weight divided by 9650. So what we can write, one more formula over here, it become equivalent weight divided by 96500 into I into T. And there is one more thing, which is eta. Eta is the efficiency, current efficiency. Current efficiency. This is the full formula of this Faraday's first law. Okay. So question will be like current efficiency is 80%. So value will be 0.8. And accordingly, you're going to solve how much the weight will going to dissolve or deposit it. Any difficulty in this? Yes or no? Tell me. Fine. Here only we can discuss Faraday's second law. Second law is basically the improvisation of the first law only. They're saying if you pass an equal charge between the two different electrolytes, then they will deposit a like the equivalent weight of the both compound. So you have two different electrolytes. Okay. So weight of one electrolyte will be what? Weight of one electrolyte will be E96 or say E1 9650 I into T. And you're saying same charge is going to pass with the second compound as well. So W2 will be what? E1 96500 into I into T. If same charge will going to be passed, means IT is same. If you take the ratio, this IT get cancel out because that will be same. 9650 cancel out. So you will get weight deposited will have the same ratio as their equivalent masses. This is your second law. And when the charge remains same, when would the charge will remain same? Like you pass the charge through different electrolyte. What is the possibility that those electrolytes should be in which position so that they get the equivalent charge when they are connected in series? Isn't it? So in series, the charge is equivalent, correct? In parallel, it get divided. So for this also you can relate it. So these are the two laws of Faraday's. Now, if I ask you one question on it, any doubt before I move on to question part? Any doubt? Are you guys sleeping? Huh?
No, sir, no doubt.
No, sir.
Okay, then answer this. What mass of copper will be supplied? No, I use this. Will be deposited, not supplied. Will be deposited on an electrode if current of 96.5 ampere is passed for 1 hour to 1 aqueous copper sulfate. Do it. Tell me. Samhed, are you here?
Yes, sir.
Okay. You also writing pre-board?
Yes, sir. They start from Friday for me.
It will start or started what?
So they'll start on Friday.
Okay. So will you going to attend that Sunday class or not? Or will you write the Monday paper?
So I'll try and write the paper. So.
Okay. There's no hard and fast rule, right? So if you feel like you should write pre-board, go for it, okay? When you had time, then you can come and write, okay?
Yes, sir.
So pre-board, like all chapters will be coming, right? In chemistry.
Yes, sir.
Yes, sir.
12th full syllabus.
Correct. Guys, you need some notes like which can help you in your pre-boards or somewhere like theoretical notes. I have some PDF and I feel like it is good for board exams. So right now I have solution, kinetic and electrochemistry PDF. So if people want, I can share with you. Huh? You
Yes,
need
sir.
or
Oh, yes, sir. Yes, I can share it.
okay. But you need to DM me. I will not going to share it in the group. The one who going to DM me, those will going to get it. I will look for other chapters PDF as well. So I will share for those as well. Okay. How many, like in physical, you have 3 chapters, right? Nothing like surface chemistry is also not there, isn't it?
Yeah, only 3.
Only 3. Then in inorganic, you have coordination compound only. P block is also
And
there.
D and F.
Oh, P block is not there.
No, P is there.
Okay. So D. Except I think what biomolecules or polymer. I think chemistry in everyday life was also not there.
Sir, polymer and chemistry and everything.
Okay, biomolecules are there. Okay, fine.
Yes, sir.
So I'll search for organic PDF as well and share with you. It contain like good theory and some previous year questions from the CBSE board. You all are from CBSE board, right? Is there anyone who's from ICSE in your batch?
Me, sir.
Me who?
Deepak.
Deepak. Okay. For you also, like it's going to help. It doesn't mean like it will not help. It will. So So your syllabus is different or what, Deepak?
No, sir, similar to this.
Similar to this. You guys also following NCRT, right?
Yes, sir.
Hmm. So in the book itself, they have removed the chapters. What
Not
does it say?
from the book, like initially everything was there, but then later on, when after CBSE reduced their syllabus, even
Uh-huh.
I did it.
Okay. But I saw somebody's book. Is it from 11th then? Because 11th NCRT now they are, publishing. They,
Use this year.
yeah,
It's
they
not in the
removed all the
textbook.
correct.
I haven't read it.
Okay. In your 12th class as well, or like just only the new NCRTs?
Our textbook.
Okay. Hmm. Okay, done, guys. So what mass of copper will be deposited on electrode if current of this is passed for 1 hour to an aqueous copper sulfate? So weight we need to find out, and that will be equivalent weight of copper divided by 96500 into IT. So what is I? 96.5 ampere into time, and it should be in second. So 1 hour means 60 minute into 60 second, this way. Correct. So if I remove this, it becomes 10 and that become 100. And from 100, it goes like this. But what is the equivalent weight? So 6636, and equivalent weight of copper we need to find. So copper mass is 63 point something. Take it 64 for a while. And 64 if I have taken, then charge is plus 2. So n factor will be 2. So that will be your answer. 36 into 32. So all of you get this or something else? What? Hmm?
Yeah, I got it.
Okay. Now moving on. One more question. One more question on it. Let's say for what time? For what time? A current of 2 ampere to be passed. A current of 2 ampere to be passed to coat silver metal on a metal object of surface area 100 centimeters square and silver coating thickness of 10 to the power minus 3 millimeter, given that density of silver solid is 10.8 gram per centimeter cube and atomic mass of silver is 108. Now tell me what time it's going to take to do this. So what is happening? Electroplating. They're doing the electroplating. So electrolysis, like one of the important application of electrolysis is this electroplating. Ooh, guys, I'll give you 3 minutes for it. That is also like more. Do it. Guys, done. Any answer? So according to Faraday's law, W equal to what? E over 96500 I into T into eta. Nothing is given. Take eta as 1. Okay. What they're asking? What time? They're asking T. Do we have I? Yes. Do we have E? Equivalent weight of AG. So that will be what? 108 divided by 1, because 1 and factor is 1 only for AG, isn't it? So that is also we need W. Okay. So W we're going to get from this density. Density is what? Weight upon volume. And how are we going to get the volume? So surface area is given to us, thickness is given to us. Volume will be what? So weight is density 10.8 into volume. Volume is surface area into thickness, which will be 10 to the power minus 3 divided by 10. Why? Because it's in mm. So in centimeter you need to convert. So that comes out to be what? 0.108. That will be your weight. Correct. Put it over here. So 0.108 equal to 108,965,002 ampere current time. So time from here will be what? So this 10108 get cancelled out. This get cancelled out. You're left with what? 965 divided by 2 into 10. Correct, no? Right? So half of 96.5. So it will be what? 43.25 second. 43 or 48? 48. 48.25 seconds. So that will be your time. So anyone who got this? Yes or no? Yes or no? Have I lost my connection? No, no.
No, sir.
No,
I didn't get
sir.
this because of calculation.
Okay. Tell me guys if you have any doubt. Now in electrolysis, there is one thing which like important also, and questions will be there. And that is like discharging. We know if say this is your electrolytic cell for electrolysis, right? positive, negative, positive. So that part is basically the anode, positive part, and that part is cathode. Okay, cation will move on to cathode part, and anion will move on to anode part, right? And for anion, oxidation happen, and for cation, reduction happen. Correct. Now the thing is, if you have more than one cation in the solution, so solution have more than one cation, cation 1, cation 1, cation 2, right? And similarly, you have more than one anion, anion 1 and anion 2. So which anion will go first get oxidized, and which cation will go first at the cathode and get reduced? How are we going to decide? And this is basically the preferential deposition or preferential electrolysis that comes under the preferential electrolysis. Okay. Now the basic funda is at anode oxidation is happening. So if oxidation potential is more, then deposition is more. If more the oxidation potential of oxidation potential of what? Anion, then it will go at the anode faster and then deposition happen. Similarly, if E naught reduction potential is greater of cation, then it will go faster towards the electrode and get deposit. Deposition will be more. So you need to check the electrode potential, right? More the electrode potential of particular anion or cation, then more will be their deposition. So I'll give you the order, like if I'll give you the order for the cation and the anion. In that order, you need to deposit them. So I'll be writing first for cation, which will going to deposit faster. So if potassium is there, then before potassium, calcium will going to deposit. Before this, sodium will going to deposit. Then magnesium, then aluminium, and then comes the water. If zinc is there before water, zinc will going to get reduced. Then iron, then H plus, then copper, Ag plus, and Au3 plus. This is how the cation reduction part will be there. So this is the increasing order of ease of reduction at cathode. Okay. One more thing, like I need to give you is this, but so like always remember at cathode or anode, if water is there, don't think like H plus will going to get oxidized or like get reduced and OH minus get oxidized. Always at cathode and anode, water only get oxidized or reduced. So if cathode part is there, so then H2O will going to reduce, and what it going to form? So H2O will take the electron and form H2 gas and OH minus. So balance it out. So this is how you're going to get. Okay. And if it is anode, then we're going to see the anion. So what will be the order of anion in that case? So sulfate will be the least, then nitrate, then H2O, then OH minus, Cl minus, Br minus, I minus. This is the anionic mobility part, you can say, or tendency of ease of oxidation at anode. Okay. And if potential is given, always go for the potential part. More the potential. If it is oxidation, then see the oxidation potential more, then it will go first. And if reduction is there, see the reduction potential, then it will go first. Okay. But in that only, there is some special case, 2 special cases I'm going to give in your syllabus, which is there, that you need to remember. Like even though their oxidation potential is higher or reduction potential is higher, they will not going to reduce or oxidize first. And what I am talking about? I'm talking about for water with the chlorine ion. Okay. How? Let's see those exceptions. So you can write, I hate this word, but you can write this as exception. Basically, their thermodynamic stability and the kinetic stability matters, due to which what we assume like it should get deposit, but it will not going to deposit, uh, and the other will going to get deposit. Okay. So the thing is, if you take the electrolysis of brine, okay, if you take the electrolysis of brine, then you should get the oxygen because Cl minus is there, and obviously if you are using Cl minus and water will be there, so Cl minus. Okay, just write down. Let's see like what I'm saying. So electrolysis of brine we are talking about. Electrolysis of brine. So cathode part, we have two things. What? We have Na plus and water. So if you go up, what are you going to see? Which will going to easier? So basically what going to happen? H2O will going to easy give the what? H2. So if you see at the cathode, H2 will going to be obtained. Right? But in the case of anion, okay, so in the case of anion, anode will be there. Now we have two cases. What? Water molecule is there. So if water molecule get oxidized, it will give you what? Just a minute. That only, na? Okay. Okay. Yeah. See, water giving you what? It will give you H2 is there, right? So H2 gives you O2 and 2H plus, let's say half O2 and 2 electron. Correct. It should be there. And chlorine is also the chloride ion. So if chloride ion get oxidized, it's going to form Cl2 and 2 electron. Now, which will going to give you the, yeah, which will going to give you, of which either the H2O should be oxidized or Cl minus should be oxidized, that we need to decide. So if you talk about this oxidation potential, E naught of this comes out to be minus 0.83 volt. Okay. I think it's not 0.83, it's basically minus 1.23. 1.23 volt. Correct. And if you talk about E naught of this, Cl minus to Cl2, that is minus 1.35 volt. 35 volt. Now, anion will give you the like competition. In cathode, we are sure like H2O will going to get water reduced and give the H2 gas. So if I write for the cathode part, so it will be what? 2H2 will going to reduce, gives you 2 electron and makes you what? H2 and 2H minus. And for this, E naught is basically minus 0.83 volt. Now make a cell of this and make a cell of this. What do you think? What value you going to get? So if you make a chlorine, this wala cell together, it comes out to be what? Minus 0.83 and minus 1.35. Okay. And that value will be what? 53831 and 2.18. So minus 2.18 volt. That is like when Cl and water is there and water. And if you take water, So if you take water, H2 and H2, then it should be what? Minus 1.23 and minus 0.83 volt. And that comes out to be what? If you add 6, 10 to minus 2.06 volt. Now more spontaneous will be what? This. Like on both the electrode, water should get oxidized or reduce, and accordingly it should produce hydrogen and O2. But it will not going to be there. Why? You will be seeing Cl2 will going to produce more. Cl2 will going to produce more. When you do the electrolysis of brine, O2 should obtain, but instead of O2, we get Cl2. And the reason is because kinetically Cl2 is more stable. So the rate of oxidation of rate of oxidation of Cl minus is more compared to rate of oxidation of water. So it just like I used to say, it's just like when you do the competitive preparation, no, don't think like smart people will going to get selected. No, the one which is doing the hard work, they will going to get selected. So it feels like it has the electrode potential lower, or you can say higher compared to the oxidation potential. So electrode potential of this water is higher compared to Cl minus. Still, it is not getting evolved in a large amount as the Cl2. So over here, what we do in order to get the significant amount of O2 production, we increase the current. If you increase the current, then charge will going to pass more, and if charge going to pass more, then more evolution will be there. So in order to do that, we do the potential over voltage. So over voltage concept will be there. Over potential concept is there. Now, if you are increasing the potential difference, no doubt O2 concentration will going to increase, but it will more significantly increase the production of Cl2. Again, it is get benefited, like over potential concept get benefited for Cl2 than compared to O2. Okay, are you getting it? What I'm saying, guys? So in this case, whatever the preferential charge deposition we have seen, we have the order. So according to that order, water should be like oxidized first and liberate the O2, but it is not happening. Instead of that, Cl2 getting liberated in a good amount. So you can see the liberation is there, but the amount is lesser for O2. That's why it is not very significant. So that exception you need to remember. Okay. In electrolytic part, this is what we have. Then we can move on to the next part. Is there any doubt so far? Tell me. Any doubts?
No, sir.
Clear? Okay. Then we can move to third part of this chapter, which is electrolytic conduction. So if we talk about conductor, we have two type of conductors, metallic conductor or metallic conduction, because we are studying the conduction. So let's talk about metallic conduction, and this chapter contains the electrolytic conduction. Okay. So this is due to the electrolyte, and this is due to the metal. Two type of conduction are there, but our focus on the electrolytic conduction. So in exam, they can ask you the difference between the metallic conduction and electrolytic conduction. So go through it and they can have it, right? If we talk about some other terms are being used like resistance. Resistance is what? Rho L by A for metallic conduction. And same analogy we can use for the electrolytic conduction as well. So this rho is what? Resistivity. Okay. And L by A is what? Cell constant. Now reverse this, like 1 by R is equal to 1 by rho A by L. Send this A by L to other side. It become 1 by rho equal to 1 by R L by A. Now, what is this 1 by rho? 1 by rho is basically the, earlier it was resistivity, now it become conductivity, opposite of resistivity. And 1 by R was resistance, now it become conductance. And that is again cell constant only. So cell constant we use like G star. For conductance we use G, and for conductivity or specific conductivity we use kappa. Okay. So basically you have one formula. Kappa is G into G star. Okay. If electrolyte is same, your cell is same, then cell constant remain same. Are you getting it? Like not electrolyte, yeah, electrolyte same. It can be of different concentration, but cell constant will depend on the length and the area of cross section. This area of cross section should be of those electrode. Like keep in mind the area of cross section of these electrode will be what? First, we are talking about the common area, and it should be dipped. It should be properly dipped into the electrolyte. So the common area which is overlapping with each other in these two electrode, and it should be dipped. So that common area you're going to consider only. Okay. And L is the distance between these two. You cannot take this wala area. I didn't shade it. Why? Because it is not dipped. Just assume like this is not dipped area, and that is not going to be included. So you're going to take the area which is common, and that should be dipped. This is it. Now, conductivity shows the additive property. Like if K total we need to find out, you can add the conductivity of all the electrolyte which is present into the solution, even of the water as well. That is what the conductivity total of any electrolytic solution. With that, you're going to see that that conductance also become the same thing, because kappa is what? G into G star. G into G star. Now, if G star is cell constant, it remains constant, right? So what are you going to get? G water, G star. So G star cancel out. You get conductance of electrolyte become same. Summation of conductance of all electrolyte, isn't it? And what is conductance? Reciprocal of resistance. So resistance total will be what? 1 by R1, 1 by R2. And if you see this, it feels like all the electrolyte in the solution will be what? Will be say something, guys. What you are seeing over here? Resistance. What is this formula?
Parallel.
Yes. So the electrolyte behave like they are connected parallelly to each other into the solution. If you have a mixture of more than say 2-3 electrolyte, so they will just behave like they are parallelly connected with each other. Clear? See, if nothing is mentioned and 2-3 different type of electrolyte is there, what you can do? You can neglect the water contribution. But if they give you the water contribution, right, then you're going to account it. Okay. So can you do a couple of questions if I ask? Tell me. Calculate conductivity contribution of AgCl if conductivity of saturated aqueous solution of AgCl is 10 to the power minus 6 Simon centimeter inverse. And given that conductivity of water is 5 into 10 to the power minus 8 Simon centimeter inverse. Yes, tell me. So what will be the conductivity contribution of AgCl? Give the answer. Done? Is it that difficult? Guys, either you are not able to apply the formula or you are not able to do the mathematics. What is the difficult part of it? So we have seen conductivity of total will be what? Conductivity of electrolyte 1 and conductivity electrolyte 2. We have two electrolyte AgCl and water. So conductivity AgCl plus conductivity water. That will be total conductivity. Now, total conductivity is given to us. Aqueous solution AgCl is 10 to the power minus 6. That is given to us. KAgCl we need to find out. K water is also given to us. So can I write 0.05 into 10 to the power minus 6? Then KAgCl will be what? KAgCl will be 10 to the power minus 6 minus 0.05 10 to the power minus 6. So that will be 1 minus 0.05 10 to the power minus 6. So what left? 0.95 10 to the power minus 6. Isn't it? 9.5 10 to the power minus 7. Yes or no? Guys,
Yes, sir.
okay.
Yes, sir.
Now, after that, we have molar conductivity. So molar conductivity is basically lambda m. Okay. So there are two formulas that you need to remember in this. Lambda m can be calculated as kappa times 1000 by concentration, which is molarity. So that is one formula, but this is in CGS. Okay. So if lambda m you are calculating in Simon centimeter square, molar, yeah, that will be molarity unit, right? So, but liter is there, no? Yeah, that becomes something more. Mole inverse. Simon centimeter square, mole inverse. If the unit you're going to check it. But the unit if you're going to take as Simon meter square, mole inverse, which is in SI, then formula becomes kappa divided by 1000 into molarity. Keep in mind, guys. Accordingly, you're going to use it. Okay. So don't mix it up. You might have studied this one, but both also you have studied, but most of the time students only use this. They see the molar conductivity, they go for it. Similar to molar conductivity, there is one more part, equivalent conductivity. And it also has the same kind of formula only. But there is one more difference only. What it is? Instead of molarity, we will be using normality. So lambda equivalent will be what? Kappa times 1000. Now instead of molarity, normality. Similarly, kappa by 1000 normality. This will be in SI and that will be in CGS. Okay, unit will be like Simon centimeter square equivalent inverse, and that will be Simon meter square equivalent inverse. And what will be the relation between these two? So you can take the ratio of, so it comes out to be lambda equivalent is lambda m over n factor. For a same electrolyte, the relation between the equivalent conductivity and molar conductivity will be this one. Clear? I think you must have done it, right? Can I ask one question directly? Okay, then answer this. Resistance of a conductivity cell filled with 0.1 molar KCl solution, and that is 100 ohm. Now, if resistance of same cell when filled with 0.02 molar KCl solution is 520 ohm, then calculate conductivity, cell constant, and molar conductivity of 0.02 molar KCl solution. Given what is given? Given is kappa of 0.1 molar KCl solution, and that is basically 1.3 Simon meter inverse. Do this question, and I'm just coming back. Okay, that much of time you have. Guys, done? Any answer?
Is it
On
248?
248. Okay. 248 what? Because they are asking three questions, right? Conductivity, cell constant, molar conductivity. So what it is?
Oh, molar conductivity. 1 minute, I'll tell you the other two.
Hmm.
Conductivity 0.00248.
Conductivity 0.00248. Okay. Wait. So what we can do? Resistance of a conductivity filled with 0.1 molar KCl solution. Okay. Is 100 of. So what is kappa? Kappa is G into G star, right? And we have resistance. So basically we have conductance because conductance is nothing but 1 by R. So G value is 1 upon 100 given to us. And G star need to find resistance of a conductivity cell filled with this. Okay. Now, if you see 0.1 molar KCl, conductivity is also given to us, which is 1.3. So 1.3. So from here, G star we have calculated. What it is? 130. Correct, no? Yes. So 130 we have calculated G star. Now for second cell, which has 0.02 molar KCl. For this, conductivity will be what? G into G star again. You have G star. What is G? So again, 1 by R. So 1 by 520 into 130. So it comes out as 1 by 4. So you have calculated conductivity as well for this solution. Fine. So we have calculated conductivity, we have calculated cell constant. Then lambda m. Lambda m for 0.2 molar. For 0.2 molar. Okay. Now see this conductivity we have calculated that will be in unit of Simon meter inverse. It means the lambda m which we going to calculate that will be in Simon meter inverse mole, sorry, not meter inverse, meter square mole inverse means SI unit. So the formula will be what? Kappa over 1000 into molarity. So kappa value is 1 by 4, which is 0.25 over 1000 into molarity is 0.02. So it will be what? 0.25 divided by 20, isn't it? So their value will be what? 0.0125. Correct? Correct, no? So this is what you're going to get. Lambda m. So you need to like figure it out which formula you need to use. Then only you can reach to the correct value. Did you check where you are mistaken?
Yes, sir. Calculation.
Okay. Now in this, there comes the variation of the conductivity, like how the conductivity will going to change if you are going to change the concentration. So that variation you need to look for. Okay. So variation in kappa with concentration. So I'll just give the few points about it. Say on dilution, if you are diluting the solution, so on dilution, if you increasing the dilution, then concentration will going to decrease. So you can say other word concentration decreases, then it will decrease the kappa. Okay. For both, for weak electrolyte or strong, whatever it is. For both, it will going to decrease. Okay. But if you talk about lambda m or lambda equivalent, then what will be happening? So the same thing on dilution, if you talk about, increase dilution, decrease the concentration, then lambda m or lambda equivalent, both will going to what? Increase. This is not ratio. This is like or like lambda m and lambda equivalent. They both will going to increase. Fine. And from here only we take that mathematical representation experimentally if we derive it. So if we draw the graph between lambda m and root concentration. So for a strong electrolyte, it comes out this way. And for weak electrolyte, it comes out this way. So this is for strong electrolyte. And this is for weak electrolyte. And then if you extrapolate it, this. So there will be one value which is known as lambda m at infinite dilution. So for a strong electrolyte, experimentally you can calculate the lambda m at its infinite dilution. But for weak electrolyte, you cannot get it. How much you try to extrapolate this graph, it will not going to intersect this lambda m. So infinite dilution, you cannot calculate the lambda m for the weak electrolyte. Experiment. And since we cannot calculate experimentally the lambda m naught for weak electrolyte, we use Kohlraasch law for it. So Kohlraasch law is basically used to calculate lambda m naught for weak electrolyte. So what we going to get from calculating lambda m naught? So in the case of a strong electrolyte, there is a relation how you going to relate the molar conductivity. So that is molar conductivity at infinite dilution minus B times root C. And what is the name of this equation? Anyone? Anyone? What is the name of this equation? Huh? Debye-Huckel-Onsager equation. These all are scientists, Debye, Huckel, and Onsager. They give this equation. Okay, like how for a strong, and this is for strong electrolyte, for strong electrolyte. So if you know the lambda m naught, you can calculate the lambda m for that strong electrolyte. Can you see like lambda m naught for a strong electrolyte is increasing? Why? Like try to understand for weak electrolyte. Try to understand for weak electrolyte. Lambda m is basically the molar conductivity, like the conductivity from the ions. It's going to be produced from the ions, obviously the conductivity. And for 1 mole of substance, we are calculating. Or you can say 1 mole of ions is there, right? So for weak electrolyte, we know if you increase the dilution, you are decreasing the concentration. And from Oswald dilution law, on increasing dilution, the more dissociation will going to be happen for the weak electrolyte. And if weak electrolyte dissociating more, then it's going to produce more ions into the solution. More ions obviously will going to increase the conductivity of the solution, which is the molar conductivity of the solution. So for this, we get to know if you go back, concentration is decreasing, means dilution is increasing. Dilution increasing, alpha increasing means number of ions will going to increase. And for weak electrolyte, we can see how exponentially there is a rise in the molar conductivity. Correct? Correct. But sir, if you talk about a strong electrolyte actually the one which dissociate into the ions completely. So their ion will not going to change. The number of ions will remain same. In the weak electrolyte, yeah, you told like, okay, number of ions will going to increase, the conductivity will going to increase. What is happening in the strong electrolyte? Like as you diluting it, it is also increasing in terms of lambda m. So can anyone tell me what is happening in that strong electrolyte? So that the molar conductivity of a strong electrolyte is also increasing. Huh? Huh? Any idea? No, nothing. See, that increment is very less. Though the increment is there, but it is very less, first of all. Okay. So that much schemate will not going to be seen as we are seeing in the case of weak electrolyte. But when we talk about dilution, so in dilution, basically solvent molecule will going to increase. And if solvent molecule will going to increase, the dielectric constant will going to increase. And that dielectric constant will separate these ions more. More separation of ions will be there. It means the force of attraction between these ions will going to be lesser, or you can say your solution viscosity decreases. So that viscosity basically, which were earlier producing a mobility friction, or you can say like uh, what mobility is basically the conductance, right? If ions will going to move freely, the conductance will be more. So if you increase the dilution, the separation become more, or you can say the force of attraction of ions will going to be lesser. This increase the, and this is the reason, like this increase the mobility of the ions and hence increase the conductivity. So this change will going to be there. That's why the strong electrolyte conductivity will going to increase on dilution. Are you getting it? Now this B value, they can ask you about this B value. What is this B value and how it going to be changed? So B value is basically a constant, and this constant is depends on nature of electrolyte. How? Depends on nature of electrolyte. So if you have similar type of electrolyte like KCl, if we talk about NaCl, you talk about. So these are 1:1 type of electrolyte. They're same. Their B value will be same. Value will be same. And similarly, if I take some other type of electrolyte, like let's say BaCl2 is there, CaCl2 is there. So these are 1:2 type of electrolyte. They are also same in nature. So their B value also be same. So that is the one part of B, depending on. Fine. They also depend on this B value also depend on temperature. If you increase the temperature, then the friction or viscosity will going to decrease, you can say. So directly you can say on increasing the temperature, B value will going to decrease. Okay. Because on increasing the temperature, viscosity will decrease, conductivity will going to increase. So if you want to increase the temperature, this value should be lesser. Then only it's going to decrease. Otherwise, the subtraction is there, then it will like change the value. So that is the one part. Dielectric constant as well. Dielectric constant. If dielectric constant of solvent will going to increase, then it will decrease the B value. So these are some factors on which B value depends on. There was one thing which I am saying, like from the graph, we can calculate the lambda m naught for a strong electrolyte by extrapolation of the graph, but we cannot get the lambda m naught of weak electrolyte. And for that, we use Kohlrausch law. So let's see Kohlrausch law. So what is this Kohlrausch law? Kohlrausch law. The full name is Kohlrausch law of independent migration of ion. So if you dilute the solution that much, like all the ions get free from, like first of all, the electrolyte get completely dissociated. If it is weak or strong, you need to dilute the electrolyte as such, like it dissociate completely into the ions. And then you dilute it as much as like there's not going to be any interaction between the ions. So all the ions moving freely on their own. So whatever be the conductivity of those ions, it's going to be solely because of those ions only. That's why this independent migration is there. So it's basically the conductivity of the ions. No matter whether your ion is coming from weak electrolyte or a strong electrolyte, the conductivity will remain same at infinite dilution. So if I say conductivity at infinite dilution, molar conductivity infinite dilution of NaCl will be molar conductivity of infinite dilution of cation plus molar conductivity of infinite dilution NiN. Say for molecule, the big lambda we're going to use. For ions, we're going to use small lambda. Let's take some weak electrolyte. So molar conductivity of acetic acid. So that also summation of molar conductivity of acetate ion and molar conductivity of hydrogen ion. Okay. And if I say molar conductivity of HCl, then molar conductivity of H plus ion and molar conductivity of Cl minus ion. That is how you're going to write. Now this molar conductivity of H plus and this molar conductivity of H plus, they are same. No matter if it is coming from weak acid or HCl, they are same only. Similarly, this Cl minus and this Cl minus, they are also same. Okay, but the condition is it should be at infinite dilution. So this is in terms of molar conductivity. Like in terms of equivalent conductivity, if I write, so for equivalent conductivity, you're going to write like NaCl I'm writing. So that will be lambda equivalent Na plus plus lambda equivalent infinite dilution at Cl minus. There is one thing, like the difference you're not going to see in this 1:1 part. Different will be seen when you take lambda m naught of BaCl2. Let's take BaCl2. So what are you going to get? You're going to get lambda m naught of Ba2 plus twice of lambda m naught of Cl minus. But if I write lambda equivalent of BaCl2, then I will be writing lambda equivalent of Ba2 plus lambda equivalent of Cl minus. Can you see the difference between these two? Can you see? Find the difference. So we are not using 2 over here in the case of lambda equivalent. Why, sir? See this. What is the relation between lambda equivalent and lambda m? This is the relation. So can I say lambda equivalent of BaCl2 will be lambda m naught of BaCl2 divided by n factor, which is 2. So what is the lambda m naught of BaCl2? This. Put it over here. So that becomes lambda m Ba2 plus twice of lambda m Cl minus lambda naught divided by 2. So if you write it individually, it becomes what? Lambda m Ba2 plus by 2 plus lambda m Cl minus. Because from 2 to 2 cancel out. Isn't it? What is this? Lambda m naught of Ba2 plus by 2. This is lambda m divided by n factor, which is lambda equivalent of Ba2 plus naught. Plus, what is this lambda m naught Cl minus? If I say 1 is there, then it is again divided by n factor. It again becomes lambda equivalent of Cl minus. So that's why. So when equivalent conductivity is there, we will not going to write the stoichiometry, but molar conductivity is there, then we're going to write the stoichiometry in Colruyt's law. Am I clear, guys?
Yes, sir.
Okay. So just give me a minute. We will be doing a couple of questions on it. And then we will wind this up. Just a minute. There's one more thing also, like you can calculate the alpha degree of dissociation in terms of this. So molar conductivity at any concentration divided by molar conductivity at infinite dilution. This is how you're going to calculate alpha. In terms of equivalent also you can calculate same way. So some of the question has been seen on this as well. So that alpha you need to remember. Okay, solve this. Solve this question. If you have lambda m naught or BaOH whole twice 457.6, okay, lambda m naught of BaCl2, that is 2406, lambda m naught for NH4Cl, that is 129.8. Now find lambda m naught of NH4OH, also lambda equivalent naught for NH4OH. Good. Simple only. Yes, guys, any answer? So by using these three, you need to make what? NH4OH. How you can do it? So you need to get this first, NH4Cl. And with this, you need to add this BaOH whole twice. Correct? But you need half of, like, you don't need this OH minus twice, right? You need one OH minus. So you can make it half of it. Then if you subtract BaCl2, okay, then also you need like what? Half of it. Why? Because only one Cl need to be subtracted, but they are two Cl. So half of Ba will automatically get subtracted from here. Correct? This is what you need. So what is the value of NH4Cl? 129.8 plus for BaOH whole twice 457.6, but you need half of it minus 240.6, half of it. Solve this. What are you going to get? And the lambda equivalent will be what? Lambda m naught divided by n factor. N factor of this one only. So there will be same lambda equivalent of this will be equal to lambda m naught of this only. Get it? Correct? Yes or no? Any guys?
Yes, sir.
Now, the molar conductivity of acetic acid at infinite dilution is 390.7, and for 0.01 molar acetic acid is 3.907. Okay, both are of the same unit only. Now calculate pH of acetic acid. So what will be the pH of acetic acid? Then you need to find. Do it. In that last section left, which is batteries. So that is more theoretical only. But we have one more class, and kinetic is there. So we can take that part in that as well. If you want to end the session now, we can. So most of the part we have covered, only that battery section left in that. So if you say so, we can continue in that next class. No issue.
Oh, yes, sir. Can we?
What?
Oh, yes, sir. Can we continue the next class after this? After this?
Sure. So battery section is there, and the application of that is very simple, like corrosion and all. Battery we have two type: primary battery, secondary battery. Okay. So if you give a reading to it, that also be fine for the class. If from past couple of days, temperature went down, right? Or is it me only feeling it? What?
There's the cyclone in Tamil Nadu, that's why.
Oh, okay. And that is also like because of December also. Typical winter thing. So this rain thing, which is happening like from the past couple of days, is because of cyclone only.
Yeah.
Okay. Guys, calculated. So basically, what you need to do, you need to calculate the pH of acetic acid. So acetic acid is a weak electrolyte. So you need to dissociate partially. It gives you CH3CO minus and H plus. So if I say C is the concentration, so at equilibrium C minus alpha, C alpha, and C alpha. So what we need for the concentration of H plus? We need alpha. And for alpha, we have seen one formula, lambda m at any concentration divided by lambda m at infinite concentration. So infinite dilution is this, and for 0.1 molar of this concentration, the lambda m is this. So 3.907 divided by 390.7. Correct? So if I remove this, take 100, it will be 1 by 100. So that is 0.01, right? Then what will be the concentration of H plus? H plus concentration C alpha. C is 0.01 into 0.01. That comes out to be 10 to the power minus 4. So pH will be what? 4. Correct, no? Minus log 10 to the power minus 4. Yes or no? Tell me. So pH will be. So if you have any doubts so far, you can ask. This is what we're going to keep for today. As I said, like we left with that battery part, as we have already done. Fair enough.
Yes, sir.
Yes,
Any
sir.
doubt?
No, sir.
Okay. Anyone else? Samhit, Deepak, Manal.
No, sir.
No, sir.
Okay. So we can end this session now. We will be having this one last chapter, and this last section of this chapter we can take it in the next class on Sunday.